Welcome everybody, and welcome to the final to lecture number 3 in the series by Guedj from the Institute of Mathematics de Toulouse. Thanks, Vincent, for your third lecture, and the title is Pluripotential Kaehler-Ricci flow.
Thank you, Claudio. Okay, so today I will make a connection or stronger connection to the set of lectures by Valentino by discussing a few issues around the behavior of the Kaehler-Ricci flow. So as Valentino recalled you, the Ricci flow introduced by Hamilton in the early 80s is the following evolution equation. And if you pick a starting metric, which is Kaehler, then this Kaehler property is preserved along the Ricci flow. Hence, in that context, this flow is named the Kaehler-Ricci flow. So as you're probably aware of, there have been a lot of successes of the use of this Ricci flow, for instance, in classifying three-dimensional closed Riemannian manifolds by the work of Perelman. Many other successes that I won't mention, actually. And in the Kaehler context, one hope is that one may use in a similar fashion these evolution equations in order to help and classify complex algebraic varieties. And even further, possibly classify Kaehler compact manifolds. And even outside of the Kaehler world, as was a bit discussed by Anna in her lectures, one might hope and study different flows or similar flows, like for instance, the Chern-Ricci flow, in order to try and say something about the classification of compact, complex manifolds that are not necessarily Kaehler. Mm-hmm. So today, one point I would like to emphasize is the need to define and study efficient notions of weak Kaehler-Ricci flow on mildly singular varieties. So focusing today on the Kaehler context. And what I'm going to discuss is based on a joint work with Wang-Qin Lu from Marseille and Ahmed Zeriai from Toulouse, where relatively recently we have developed an analog in this parabolic context to the theory developed by Bedford and Taylor on the elliptic side. Okay, so let me first catch what Valentino explained. So here, X is a compact Kaehler manifold of complex dimension n. And we fix initial data, initial Kaehler form omega 0, and study the evolution equation, this Ricci flow. So by comparison to the Riemannian settings, there's just a normalizing factor 2 that is a slight difference with the usual Riemannian case. So this is the evolution equation. And as Valentino explained, it turns out that the situation is much simpler in the complex Kaehler setting, namely, one of the first results that Valentino told you about is that one can show that this flow exists on a maximal interval of time, where this time interval can be computed in cohomology. So Tmax is actually the supremum of all those times t, so that the obvious cohomological constraint is satisfied. Namely, so you see this evolution equation is highly nonlinear, but at the level of cohomology, since the Ricci form of these evolving matrix omega t is always fixed and represent the first Chern class of the manifold, then an obvious necessary condition for this flow to be well defined is that at the level of cohomology, the classes remain Kaehler. And it turns out that this natural necessary condition is actually also sufficient for the flow to be well defined. This is far much simpler than what happens in the Riemannian setting. And in particular, that's a classical definition, the flow exists in infinite time if and only if the canonical bundle of the manifold has a certain positivity property, which is called nef, which simply means that the cohomology, the first Chern class of this canonical bundle, is a limit of Kaehler classes. In that case, when this canonical bundle is nef, one says that the manifold is a minimal model. And here, if X is smooth, one speaks of a smooth minimal model. Okay, so just a few words, because Valentino has explained this at length in his last lecture, about a program proposed by Song and Tian in order to use the Kaehler-Ritchie flow to try and classify complex Kaehler algebraic varieties. So one of the major issue in this context is to understand what happens for this evolving matrix as you approaches this maximal existence time. And ideally, what one would hope, and that was devised by Song and Tian, is the following. So at first, one tried and showed that this the manifold equipped with this family of metrics converges in a sense to be made precise to a mildly singular model, X1, say, and equipped with a limiting Kaehler curve. So at this first step, the hope is that the positivity property of the canonical bundle of this new X1 are a bit better, have been improved in the process. It's necessary to expect that this new model will have mild singularities. And it's also natural to expect that the limiting current S1 can no longer be a Kaehler form, but rather a positive closed current with a certain number of reasonably good properties. So for instance, it could be smooth and a Kaehler form on a Zariski open set, and hopefully have a bounded global potential, etc., and so on and so forth. Then the next step would be to try and restart the Kaehler-Ritchie flow on this X1 with this slightly degenerate initial data S1. And then one tries and repeat this operation finitely many times. And the hope is that in finitely many steps, one reaches a model XR, and though with a limiting current SR. And the hope is that in finitely many steps, XR has become a minimal model. So it's no longer smooth, but the hope is that the canonical bundle of XR is nef. And therefore, if one can make sense of the Kaehler-Ritchie flow on that minimal model, then the new maximal existence time will be infinite, and one hope to then study in the long run the evolution of this new normalized Kaehler-Ritchie flow, and show that at the limit it converges to a so-called canonical model of the original data, and though with a canonical metric. So this is a piece of the program of Song Tian, which corresponds to one major case that has been discussed by Valentino. So I don't want to insist any further on the remaining situations because they were a bit explained by Valentino in his last lecture. So actually, this is a huge and ambitious program. There are a certain number of known situations or progresses that have been made over the last decade. So let me discuss very briefly a few of them. First, and it was not the simplest actually of all the steps, the program is known to work on compact Riemann surfaces thanks to the work of Hamilton and Chow. In complex dimension 2, this has required far more efforts, but due to the work of many authors, and I would like to emphasize the important contribution by Jensen and Ben Weinkow, this is more or less complete. There are a few minor issues that are left, but the program essentially works in dimension 2. So starting dimension 3, the situation becomes more intricate, but nevertheless, there are a few informations that have been obtained. So let me mention that the starting, one of these difficulties is that you need to run the flow from an initial data, as I explained in the previous slide, which is slightly degenerate. So it's no longer a Kaehler form, it's rather a positive current. And we need to make sense of such a degenerate initial data. This actually is reasonably under control. So there have been works of many authors, especially Songtian, and together with Ahmed Zerrai and Eleonora Dinezar Wanqing Lu, we have shown how to make sense and reasonably good sense of this flow starting from very degenerate initial data. So this is done in a rather weak fashion, so there still remains to better understand from a more geometric perspective how the flow indeed converges in geometric senses at this initial time. Regarding the definition of the Kaehler flow on mindely singular varieties, then there are a few works treating this situation. So Songtian, so I'm mentioning the year of publication. So there is an important paper by Songtian. I will give the reference at the end of the slides, which has been published in 2017, but actually the preprint was came out on the archive in 2009. And this paper has been rather influential in the field. So in that paper, they succeeded in defining Kaehler flow in certain singular settings. And in a different direction with Philippe Essidieu and Ahmed Zerrai, we have developed a viscosity approach to this parabolic context in a series of papers, and then more recently with Wanqing Lu and Ahmed Zerrai, we have developed what I'm going to discuss further, the notion of a pluripotential solution in that context. So there are tools still under current development, but there are definitely tools to define and study these weak notions of Kaehler flow. And then, as I mentioned, an important issue is to try and prove the convergence either at a maximal existence time or at infinity if you are on a minimum model. And there are lots of many authors, and some of them have been discussed in Valentino's lecture. So I won't discuss this important point to this moment. Okay, so let me recall that gain in the Kaehler context by comparison to the standard Riemannian setting is that the Kaehler flow or its normalized version can be reduced to a scalar parabolic complex Monge-Ampère equation. So it looks like this. So on the left-hand side, you have the complex Monge-Ampère operator acting on a given unknown function phi t. And then on the right-hand side, you have a measure which is absolutely continuous as opposed to fixed smooth volume form. And in the exponential term, you have the time derivative of the unknown function phi that shows up, and then some reasonably smooth function both of time and x, and then a minor dependence on the function phi. So here, omega t is a reference family of Kaehler forms. H is smooth, as I said. The lambda here is a real number which depends on the sign of the first Chern class, if you are willing to consider the normalized Kaehler flow. And the unknown is this family of smooth functions, which are often called Kaehler potentials. In particular, they have strong, in the classical smooth setting, strong positivity property. So when you move on to mildly singular context, well, as I explained in the first lecture, then you can still make sense of such an equation or Monge-Ampère equation, but then there are a certain number of degeneracies. So the defining the Kaehler flow in a mildly singular context is equivalent, similarly, to make sense of the following type of complex Monge-Ampère flows. But now you are supposed, one possible way of thinking to that problem is to use a desingularization of your variety. And therefore you put back your forms on that desingularization. And now the reference forms, the reference family of forms is no longer Kaehler. So it is semi-positive. It is lacking positivity, if you like, along some exceptional divisors that lie above the singularities of the variety V. And it is big in the sense that the total volume of these forms is strictly positive. And moreover, so it evolves in time, but it doesn't cost much here to assume, given by the geometric setting, that you have a fixed lower bound independent of time, which is a semi-positive and big form. And so the whole analysis, if you like, for the PD, the nonlinear PD that we are considering, will actually take place in a Zariski open set, which is called the ample locus of this lower bound theta. The function f that shows up in this picture is smooth in that case. It is quasi-increasing in R, essentially, without entering into details, you can think that the dependence in R is essentially affine. It's sufficient for many geometric applications. And the singularities of the variety V are encoded in this density G, which looks like this formula on the bottom of the slide. So it has both poles and zeros, and the size of these poles and the size of these zeros depends on the precise nature of the singularities you need to consider. But in any case, as I explained briefly in the first lecture, what we need to consider is a situation where the singularities are locked in null, and this ensures that G is LP integrable with some exponent P, which is slightly bigger than 1. And this has a very important consequence regarding L infinity a priori bounds, as I explained in lecture 2. Okay, so that's the type of degeneracies we need to work with. And once again, if you go back in the previous slide, you see that the dependence in the right-hand side on phi is reasonably simple. So I could equally well pick something similar here. But for those of you who are used to geometric analysis or working with nonlinear PDEs, source of success quite often in this area is to embed one specific equation you're interested in into a much larger family where you have more freedom of producing method that works for this more general context. So this is exactly what we are going to do right now. So I'm going to consider this family of parabolic complex Monge-Ampère equation, and I'm going to think about them in the following fashion. So I want to make sense, to give weak meaning to solutions to such an equation, interpreting this equation as a second order nonlinear PDE on the manifold xt, which has very dimension 2n plus 1. And I want to make sense first of the left-hand side in a Bedford-Taylor style manner. So I want to impose that the dependence t goes to phi t gives me a family of bounded omega t personic functions. And therefore, the complex Monge-Ampère omega t plus idb bar phi t to the n is well defined in the Bedford-Taylor sense, as I briefly recall in the first lecture. And this allows to give a sense to this left-hand side as a nice positive Rado measure on this manifold XT. Let me maybe emphasize that in that, with that point of view, if the phi, it's important to understand what happens by approximation. So traditionally, a natural method that I'm going to follow today is to approximate the non-smooth equation by smooth approximants. So we'll need to have good convergence results in order to pass from the approximating information to the limiting setting. So here, the situation is reasonably good in that left-hand side point of view. So if the phi tj's, say, approximants increase or decrease towards the limit, then the left-hand side behavior is well understood and converges toward the limiting measure. It's also true if you have uniform convergence, or if you have a weaker notion of convergence, which is called energy convergence, that I'm not going to recall today. But let me stress maybe that one important source of technical difficulty is that L1 convergence does not suffice. As I said in the, or partly said, explained in the lecture 2, we have very good and very strong compactness type information in these families of omega t Pearsonic functions in the L1 sense. But these do not suffice in general to pass to the limit in the complex Monge-Ampère operator. So what about the right-hand side? So we are going to use Lebesgue point of view on the left-hand side. So we want to make sense of dt phi, so the time derivative of this potential. And clearly, this will be well defined almost everywhere if the dependence in time is locally uniformly Lipschitz. So it's important that you avoid imposing too strong condition at time 0. So I want this dependence to be locally uniformly Lipschitz outside of 0. Actually, as you understood, I hope from the previous slides, we need to start the flow from an initial data that might be very degenerate. So we don't want to impose too much as you approach 0. In particular, if we would have Lipschitz information up to time 0, this would impose that phi 0 should be continuous, which is a priori not clear in the geometric picture. On the other hand, this is not a problem. This is something maybe I won't have time to explain, but that you should keep in mind. These Monge-Ampère flows, a bit like heat flows, have a very strong smoothing type properties. So you may start from a rather poorly regular initial data phi 0, and these Monge-Ampère flows have the tendency to smooth out immediately in time the data that you are starting with. So let me make the following definition. A parabolic potential phi will be simply a family of omega t Pearsonic functions. I don't have space to read my, which is locally uniformly Lipschitz in time, avoiding, as I explained, time 0. We will usually actually ask for this family of parabolic potentials to be bounded, but let's keep that for later. So actually, so this definition suffices to, if I add the fact that the family is bounded, to give sense to the right-hand side, as I just explained, and to give sense to the left-hand side, I explained on the previous slide. But in the approximation process, as I explained, situation is reasonably good for the left-hand side, but how to pass the limit on this right-hand side if I'm approximating the situation by smoother equations. Well, the difficulty lies in this time derivative, dt phi j, say, if phi j are the approximants. I want to be able to pass to the limit in the time derivative. And in order to do that, I will impose a slightly, or I will try to capture a slightly stronger time dependence property. Namely, I would like the property that the dependence in time is essentially concave, so locally uniformly semi-concave. If you like, semi-concave means that the second time derivative, rather than being negative, that would correspond to concave, is actually uniformly bounded from both. Okay, and as I just mentioned, this will allow us to get good convergence properties on this time derivative. Okay, so these point of views being explained, here comes the main result I would like to briefly discuss today. Namely, this is a result obtained with Wanqing Lu and Amenzeriai. If I start from an initial data that is just a bounded omega 0 plus function, and I assume the following regularity properties on the equation. So the function f has to be continuous in the 3 variable, quasi-increasing in the last variable, and locally uniformly semi-convex in the first and third variable. Then I take this density G for the geometric purpose that will be in LP for some p bigger than 1, and I want to impose, and this makes sense also in the geometric context, that the set where G vanishes, if you like, that would correspond to the poles of these Monge-Ampère flows, this should have measure 0. Then there exists a unique parabolic potential, phi, which is locally uniformly bounded. So you can actually see it is essentially globally uniformly bounded. The only problem is what would happen at the maximal existence time. Okay, so if you stop just before the maximal existence time, capital T, then you have a completely globally uniformly bounded family. So it's a kind of C0 estimate, if you like. Then the second piece of information is that under that mild regularity assumptions on the equation, then the solution will be locally uniformly semi-concave. And here one should avoid what happens at 0. And finally, phi is a pluripotential solution of the equation, of the parabolic equation, with which with fixed initial Cauchy data. So at time 0, at least in the L1 sense, you have that phi t converges towards phi 0. So as you will see in the next slides, actually the convergence at 0 is much better than L1. It's, in a certain sense, the best one can expect. If, for instance, phi 0 would be continuous, then phi t would actually uniformly converge towards phi 0. Okay, so that's the main result, which says, if you like, that these general complex Monge-Ampère flows, which in particular contain, as a special case, the Monge-Ampère flows that show up for the Kaehler-Ritchie flow or normalized Kaehler-Ritchie flow on mildly singular varieties, have a unique weak solution with that type of properties. So let me say just, or make a brief comments on comparison with what was known before. So first, in this influential paper by Songtian that I mentioned, they developed a theory of weak Kaehler-Ritchie flow. So for reasons that one could perhaps avoid, they needed to assume to make a projectivity assumptions on the variety, but more problematic in my sense is that they require, so from a geometric perspective, of course, you want your solution to be smooth or very nice on the regular part of the variety. So this one can achieve. I'm not mentioning this, but in the previous theorem, you can also get such high regularity whenever it makes sense. But in the case of Song and Tian, this was somehow a part of the notion of their regularity flow. And in the end, it makes the notion not very flexible to work with. So especially regarding uniqueness and comparison result. In a slightly different direction with Philippe Sidiou and Ahmed Zereli, in a series of work, we have developed a viscosity parabolic theory. And so this method, as you are probably aware, has been developed by Pierre Williams and many others in famous method in nonlinear PDEs. We have somehow adapted this method to this more geometric context and with the issues regarding the complex Monge-Ampère operator. So the method is very flexible, but the drawback is that it requires all the data to be continuous. So in particular, from a geometric perspective or for geometric applications, it makes no difference to work on Kaehler rather than projective varieties. So this is a good news. It allows one to treat the case of canonical singularities, but the situation with low canonical singularities, which is so important in the minimal model program, this is kind of a problem for this viscosity approach. So this was one, not the only one, but one source of motivation for developing an alternative methodology. Regarding smoothing properties, there has been, as I already mentioned, a lot of work, and the situation is reasonably under control. Let me mention a work by Topping, notably in complex dimension 1, by Eleonora Dinesa and Wanqing Lu, which essentially says that in the previous theorem that I mentioned, for convenience, asked for phi0 to be bounded, but one could easily extend the situation to a phi0, which is essentially an arbitrary omega0 Pearsonic function. Okay, so and my goal is to describe a bit the contents of the previous theorem, where and try and convey the idea that this preferential approach is somehow more efficient. Okay, so here's the strategy, or one possible strategy. I might say, if time allows, if time permits, I might say one word about a slightly different possible strategy. But let's start with this one, which is somehow quite natural in this nonlinear PD business. So I approximate all my data, F, which was essentially continuous, by Fj, which are smooth, G, which is in LP, by Gj, which are smooth and positive, and omega Tj, which are only semi-positive and big, by omega T, which is only semi-positive and big, by omega Tj, which are honest scalar forms. And then I end up with a nice family of smooth parabolic Monge-Ampère flows. And I want to try and pass to the limit. So I know, if you like, more or less by in the same vein as what Valentino explained to you, that these smooth Monge-Ampère flows have nice smooth solution in a fixed interval of time, independent of J. And then I try to produce a priori estimates. So it turns out that there are essentially three uniform a priori estimates that one need to establish. I will say a few words about each of them. And then we pass to the limits using this semi-concavity property that I mentioned. And more involved is then to show that the limiting guide that we obtain is the right unique object with these properties. And this requires to establish a certain type of maximum principle that in that context we call the parabolic comparison principle in order to get uniqueness. So the alternative approach I just quote is to use a Perron type method it has it is somehow a bit more technical than what I'm going to describe now with this smoothing approximants, but it has also advantages in more singular or more degenerate situation. So this alternative approach, we have developed it in a local setting with the same collaborator, with Wenqing Lu and Ahmed Zayai. And more recently, and I will give the references at the end, PhD student Quang Tuan Dan has developed that in a compact setting. So developing the same story with this different approach and treating more general geometric framework. Okay, so for the remaining or next few slides, let me assume that I'm dealing with a smooth complex Monge-Ampère flow, and I will try and produce these three uniform a priori estimates. So the first one is essentially a consequence of what I explained in lecture 2. So we can, without loss of generality, work in a finite interval of time and assume, therefore, that the reference forms, omega t, are bounded uniformly in between two semi-positive and big forms, theta 1, theta minus, and theta plus. And then what I explained in lecture 2 allows you to understand that we can find uniquely normalized or theta plus or theta minus bounded function. So sorry, theta plus or theta minus PSH function which are bounded, and solution to this complex elliptic Monge-Ampère equation. So this is, as I explained in lecture 2, because the density G is in LP for some P bigger than 1, we have a global uniform a priori bound on such solutions. And here the constant C plus C minus are just normalizing constants so that the mass on the left-hand side is the same that the total mass on the right-hand side. Okay, and then the simple observation that with this tool in hand provided by lecture 2 is that if you consider rho plus a large constant time t plus 1, or if you consider u minus, which is rho minus a large constant time t plus 1, then u plus is a super solution to the complex Monge-Ampère flow, and u minus is a sub-solution to this approximate complex Monge-Ampère flow with initial data phi 0. And the consequence of that is that as you are not defining but what means to be sub or sub-solution, but as the name indicates, the sub-solution lies below the solution, the super-solution lies above the solution. So this gives immediately a global uniform bound on the solution phi t. So you see that the bound blows up as you approach the maximal existent time, but as long as you're in a finite piece of interval of time, then you have a global uniform bound. And this constant C, I'm not making the computation, but trust me, it's not that difficult here. It depends on the LP norm of G. So this is because rho plus and rho minus do depend on this density. It depends on the L infinity norm of the initial data, the Cauchy data phi 0. This is to make sure that U plus lies above phi 0 at time 0, and U minus lies below phi 0 at time 0, and on F in a rather weak fashion, as you can see. Okay, so that's the first a priori estimate. And once again, I'm not giving the full detail, but it's not that complicated once the result from the important result from lecture 2 is provided. Now, one word about the second estimate, which is a Lipschitz control. So for that one, we need to impose this condition on the time derivative of the reference family of forms. And assuming this, the statement is like this. There exists a uniform constant C so that, if you like, phi t is, as I promised somehow, locally uniformly Lipschitz in time away from time zero. And here the statement is a bit more precise than what I said earlier, namely that as you approach zero, it is almost Lipschitz, if you like. So you have a good understanding on the way the Lipschitz constant may blow up as you approach zero. Let me maybe stress that this is essentially, so yeah, the proof goes back more or less to the work of Sun and Tian with some extra generalization that we have done with Ahmed Zariai. And let me also stress that the constant depends essentially on the same quantity as in the C0 estimate, plus you need to be able to control Lipschitz constant in time and in the last variable for the capital F. And the lower bound, I would like to stress that it is very good. So you see that the way the Lipschitz constant blows up on the right-hand side is a bit tougher, but on the left-hand side, so from below, the Lipschitz constant does not blow up very fast. And in particular, if it is an integrable singularity at time zero, so if you integrate it, what you get is that phi t stays essentially above phi zero. So for all times, as you approach zero, the way phi t will converge to phi zero is essentially from above. And then it's a nice property, a nice consequence of Paris abundancity, that if such is the case, then the convergence, as soon as you have L1 convergence from phi t to phi zero, then the convergence is actually very good. If you like, this is a general property, a general consequence of Paris abundancity. If a sequence phi j of Parisonic functions converge in L1 to some function phi, then essentially the phi j have the tendency to go below the limit. And if you know that it approximates from above, then the convergence is in a certain sense very strong. So here, I'm not going to give more details on that, but just keep in mind that this lower bound on the Lipschitz constant of phi t is extremely good and very useful actually to understand what happens at time zero. So now I would like to focus a bit on this third estimate, which I think is perhaps less usual. The previous ones were rather or more or less classical. So for that one, we need to make a further assumption on the second time derivative of the reference form omega t. And then the claim is like this. For all tx with t outside of zero, the second time derivative of phi t is bounded from above by a fixed constant if you stay away from time zero, and in the blow up, the behavior of that constant at times approaches zero is under control. It's not worse than t to the minus 2. So here, the constant depends on the previous quantities and also on an infinity norm of some of the, say, the part of the Hessian of the capital F. Okay, so this estimate, I think, is rather new in this field, and I would like to explain the proof of it, to say a few words about the proof in a simplifying setting. So let me assume that capital F is 0, and that omega t moves like for the unnormalized Ricci flow. So as Valentino explained, for the Kaehler Ricci flow, but the unnormalized version, then the forms, the reference form, if you like, the cohomology classes evolve along an affine line, and therefore you can pick reference forms that evolve affinely in time like this. So let's assume that it's meaningful from the geometric perspective, and f equal to 0. The presence of f is just a matter of technical complications, but the idea of the proof will be easier to catch that way. So under these simplifying assumptions, what I'm claiming is that actually the estimate is even better. The second time derivative of phi does not blow up. It is bounded from above by n divided by t. So you can take c equals n in the statement of the proposition and replace t squared by t actually here. Okay, so setting capital H, which is t phi t double dot, I want to prove that this quantity is bounded from above by n. Okay, so let's try and prove this in this simplified situation. And then the core of the argument is to make sure that this claim holds true. So if you apply the heat operator to this function capital H, I want to bound it from above by this quantity on the right-hand side. So let me recall that here, H is this function t phi t double dot. St will be this family of Kaehler forms, omega t plus idd bar phi t. And the Laplacian with respect to St is this usual Laplacian here. Let me first maybe assume that that the claim is satisfied. Then I want to show the bound for H. So I pick a point t0, x0 where the maximum is attained, and either t0 is 0, then we are done. H is actually bounded from above by 0, or t0 is positive, then the claim tells me that this operator should be positive at that point that reaches the maximum. And therefore, the claim tells us if you multiply the inequality by t0, tells us that H is actually bounded from above by t0 phi t0 double dot, which is bounded from above by n. So which is what we wanted. Okay, so let me now prove the claim. I want to check this, where let me recall also that under this simplifying assumption, the time derivative of the flow equation can be rewritten phi t dot equals the log of this quotient. So I'm going to be brave and differentiate twice this flow equation. So let's differentiate once. Phi t double dot, if I differentiate the logarithm, I get n times this quantity. So far, so good. Let's differentiate again. So phi t triple dots, then I will get three terms. The first term is when I differentiate the term chi plus idd bar phi t dot, and this is what I get, the Laplacian of phi t double dot. The second term is when I differentiate the denominator st to the n. And what I do get is this quantity here. And finally, if I differentiate in the numerator st to the n minus 1, I get the following term. Now, I claim that the second term and the third term are comparable and therefore rearranged that way using the following elementary inequality, which is perhaps classical, we don't know, but which I leave as an exercise. A rather easy inequality once you notice it. So you see, if I go on like this, then I can rewrite this quantity as the Laplacian of phi t double dot minus, actually the square here is 1 divided by n phi t double dot square. And therefore, when I eventually also take into account the time derivative of H, what I do get is this quantity here, which rearranges with this inequality like that. And this is exactly the claim I was mentioning. So you see, at least in this simplifying, under the simplifying assumptions, the computation and the inequality for the claim are not very difficult, and they are the key to obtain this semi-concavity, uniform semi-concavity of the solution. Okay, so once you have that, you can implement, these were the three global estimates, and then you can work on small open sets and take derivative of the equation and get higher order estimates. So the remaining pieces of the estimates are rather standard, so let me skip that. And then we can pass to the limit. So as I explained, we approximate our non-smooth flow by smooth ones. We have those three estimates here. And thanks to the compactness properties that are rather easy to get, we can extract and pass to the limit. In the L1 sense first, in the uniform sense, thanks to elliptic stability. And so the left-hand side do converge easily, and the right-hand side does converge thanks to the semi-concavity estimate. So that's the way one can prove the existence of the solution. I see that time is running fast, so let me just state the statement for the uniqueness. So the uniqueness of the solution relies on the following comparison principle. So if you have two parabolic potentials, one is a sub-solution to the flow, the other one is a super solution to the flow. And if you assume furthermore that the super solution has this semi-concavity property, and that the initial data are comparable in the right way, then the sub-solution lies below the super solution. So the proof is actually a nightmare. It's if all the data were very smooth, this is an easy consequence of the maximum principle. But due to the lack of regularity, this is really a difficult piece of information that we get here, and it takes us quite some time in the paper. So I'm going to completely skip that. I don't have time to explain it. And I was willing to give you an illustration of how to you can converge with these tools, but I think I don't have time for that. So let me skip that. Go back afterwards if you insist. But I would like to finish by mentioning the references that I've been citing on a few occasions. So first, there is this influential paper by Song and Tian. As I said, it appeared actually in 2009 on the archive. Then the method that I've been describing here today comes from that paper with Wanqing Lu and Ahmed Zeriai. The alternative Perron method technique we have been developed in the local setting shows up in this paper. And this method has been quite generalized by Quang Dan in the paper that showed up on the archive some time ago this year, where it does the same theory, but for treating big homology classes and also for a class of singularities that is a bit larger and that allows to deal with the modular space of Keller-Einstein metric of negative curvature. Okay, so this is it for me, and sorry for being a bit too fast at it. Thank you.
Yes, there is a first obvious question is, can you tell us something about the convergence?
Yeah, so that was I was giving one. I was planning to give one illustration of that here. Let me just cite that result, for instance. So if you are, it's one of the simplest setting, but that was for pedagogical purpose. So if you pick a so-called Q-Calabi-Yau variety, so let's say you replace smooth by slightly singular, but you can still make sense of the canonical bundle, and you assume it is essentially zero, say. And then we can make sense of the Keller-Ritchie flow in that context with these tools. One can further show that the evolving metrics are smooth on the regular part of the variety. And these tools that I explained somehow makes life very easy to prove the following result. If you start from any positive closed current in a fixed Keller cohomology classes with, say, bounded potentials, because that was what I explained today, then the weak Keller-Ritchie flow continuously deforms this initial data towards the unique singular Kaehler-Einstein metric in that homology class. So this limiting object is the one that somehow I mentioned the existence in the first lecture and providing with an upper estimate in the second lecture. And I'm not going to review the proof, Claudio, but the tools, the pre-potential tools, makes it very easy to show that you have a weak convergence toward this limiting guy. So I would say that in a certain sense, these soft tools that we are developing should be seen as a first step from a geometric perspective to say, okay, I have this geometric flow. I would like to understand what it does more geometrically than what we do here. But then these soft tools are a nice hint that the geometry is going to behave well or not. In particular here, it says, well, you will capture, at least in a weak sense, a unique object which is somehow canonical. And then that's not, of course, the end of the story. So then, as Valentino explained a bit, especially yesterday, then you need to make sure that you have nice smooth convergence somewhere, that you have Hausdorff convergence globally, that you can understand the asymptotic behavior near the singularities, and so on and so forth. And so I see that as somehow a good tool to detect whether you have a sense from better geometric control.
There are other questions? Because actually I wanted to ask exactly probably what you were starting discussing now. I mean, with this new technique, do you think you will be able to also to control other geometric properties of the flow, like for example, I mean, of course, bounding, scalar curve, even the old Sezultian or the Perelman thing, or then the diameter, and then other geometric quantities that could tell us a little bit what the limit is.
Yeah. So one precise point in the list of quantities that you are mentioning is the diameter bound. It turns out to be very difficult to uniformly control the diameter along the flow. What Valentino mentioned yesterday is that the situation is more or less good if you have a smooth minimal model. Then the situation has been improving lately, or very recently. But this is an important issue, and this is some project that we are working on right now. So understanding better the connection between analytic properties of the potentials and geometric properties like diameter control of the solution. And we have made some progresses on that, but the situation is strangely much more complicated for the flow than it is for the continuity method, for instance. So, and this has been, there has been an observation, I think, by maybe Foucault and Song just a few years ago, that again, for smooth minimal models, or for models with square count resolution. So an interesting situation, but where the singularities are a bit too spatial, but still they were able to get good bounds on the diameter along a continuity method. So along the continuity method, you have a nice lower bound for the Ricci curvature, which you don't necessarily have along the flow, and that's a real an important difficulty for analyzing the Kaehler-Ricci flow. But there are things to be done, and we are optimistic about at least part of it.
Any other question? Well, if not, I really would like to thank Sanford and all the speakers. Now, I think some Okay, let's stop the recording.